Assalamualaikum, my name is Amiratul Hani binti Arman and my metric number is CN240213. I will be covering for our chapter 4 estimation. In mechanical engineering, predicting how long a component will last before it fails is critical for safety and quality control. We're going to use a sample of 30 components to estimate the true average failure time for the entire population using a 95% confidence interval. First, let's look at our data. We have 30 samples, and while we recorded both temperature and failure time, our focus for this estimation is the time, which is in hours. Our sample size is n, which is 30. For our step 2, which is the calculating the sample mean, to find the center of our interval, we calculate the sample mean. We sum all the failure times from our first sample of 1,250 hours to our last, resulting in total of 3794030. When we divide that by our 30 samples, we get a sample mean, which is x bar, of 1,264.67 hours. This is our point estimate, our best single guess at the true average. Next step is by finding the sample standard deviation. We need to know how much our data varies. We use the sample standard deviation formula by calculating the difference between each data point and our mean. Squaring them and dividing by n-1, we find our variance is about 20,425. Taking the square root of that gives us a standard deviation of 142.92 hours. This tells us the typical spread of failure times in our sample. Next is determining the critical value. Since we don't know the true population standard deviation, we use the t-distribution method. We did it by doing, for our confidence level is 95%, so our alpha is 0.05, and our degrees of freedom, which is df, is by n-1, which is 30 minus 1, that resulted to 29 degrees of freedom. Looking at the t-table, we find our critical value is 2.045. This value determines how many standard errors wide our safety net needs to be. Last but not least is the confidence interval calculation. Now let's put it all together. First, we find the standard error by dividing our standard deviation by the square root of n. That gives us 26.09. Next, we calculate the margin of error. We multiply it by our calculated critical value, which is 2.045, by our standard error, 26.09, to get the 28.135 hours. Finally, we create the interval by adding and subtracting that margin for our mean, which is first is the lower limit. We get around 1,236.525, and for our upper limit, we get 1,292.805. So, what does this mean? We can say with 95% confidence that the true average failure time for these mechanical components lies between 1,236.54 and 1,292.81 hours. This range allows engineers to set maintenance schedules with a high degree of mathematical certainty.
My name is Naardina binti Kamal. My matrix number is CN240440. Today, I will present my part, which is hypothesis test. The first step is to establish our hypothesis. The null hypothesis states that the average lifespan of the mechanical component is exactly 1,200 hours. Meanwhile, the alternative hypothesis states that the average is not equal to 1,200 hours, meaning there is a significant difference. Next, we calculate the t-statistic using the t-calculation formula. Based on the sample data, we have sample mean 1,264.67, test value 1,200, standard deviation 142.92, sample size 30. After plugging these values into the formula, we obtain a calculated t-value of 2.478. To decide, we compare our calculated t-value with the critical t-value. The critical t-value for a significant level alpha of 0.05 plus minus 2.045. Since the absolute value of our calculated t 2.47x is greater than the critical value 2.045. The statistic falls into the rejection regions, critical region. Therefore, our decision is to reject the null hypothesis. In conclusion, there is sufficient evidence to state that the average lifespan of these components is significantly different from the 1,200 hours specification stated by the manufacturer. In fact, the data shows that this component lasts longer, with an average of 1,264.67 hours.
Assalamualaikum, my name is Uthm binti Aziz, my matric number CN240442, and today I will present about Chapter 6, Simple Linear Regression. For Chapter 6, we analyze the relationship between force and elongation. Based on the 30 data points collected, we developed the following regression equation: y equal negative 0.0323 plus 1.567x. In short, the slope of 1.5667 indicate that for every 1 unit increase in force, the elongation is predicted to increase by 1.567 units on average. Next, the correlation coefficient, which is R, is 0.9942. This proves there is a very strong positive linear relationship between force and elongation. The R square value is 0.9884, which means our model is highly accurate, as 98.84% of the variation in elongation can be explained by the force. To demonstrate, if the force is 5 units, our model predicts the elongation will be 7.8012 units.
So for the conclusion, this project successfully applies statistical methodologies to validate mechanical component reliability, establishing at 95% confidence interval of 1,236.54 to 1,292.81 hours for average failure times. Hypothesis testing: alpha equal 0.05 result in the rejection of the 1,200 hour manufacture specification. T equal 2.478, proving that components significantly outperform at advertised standard with a mean life of 1,264.67 hours. Furthermore, a simple linear regression analysis revealed an exceptionally strong correlation R equal 0.994 with the model y height equal negative 0.0323 plus 1.5667x, explaining 98.84% percentage of variance. His finding provide engineers with a higher precision predictive tool for maintenance scheduling, ensuring optimizing quality management and structural safety.